Across tropical Africa, intense rainfall events are disruptive and damaging to agriculture and can be especially devastating for smallholder farmers. An unanticipated storm could ruin a crop left out to dry. Unexpectedly heavy rainfall could disrupt the transport of produce to market.
Climate change is projecting that there will be an increase in the intensity and frequency of storms. That's what everybody is concerned about. Having that information means we should do something about it.
Numerical weather models to predict these events are constantly evolving and improving, but the skill of these models for the prediction of high-impact rainfall events remains fairly low across tropical Africa. Real-time observations to visualize and monitor high-impact rainfall events can provide more accurate information. Observations can even be used to make an estimation of a storm path over the next few hours. This is nowcasting and is the latest frontier in weather prediction in tropical Africa. While some countries have the luxury of radars for monitoring ongoing storms, many in the developing world do not. Through the Global Challenges Research Fund, African SWIFT project, scientists have instead been investigating and applying the use of satellite images for nowcasting over Africa, and this has been done with great success.
Satellite is an important resource. The satellites above Africa are very high quality, some of the best in the world, and they produce an enormous amount of data which hasn't really been exploited as fully as it can be to get information to people.
So FASTA, the Forecasting African Storms application, based at the University of Leeds, is taking cutting-edge research from the SWIFT project and transforming it into a practical solution. By extracting information from satellite data provided by EUMETSAT, FASTA will make nowcasting information available via an Application Programming Interface, or API. We will now demonstrate our beta version of the API. Here we have the rapidly developing thunderstorm product, which outlines storm objects identified by the EUMETSAT NWC-SAF algorithm. Given the user's location, storm objects within a given radius are retrieved from the FASTA database. The colours show whether the storms have been categorised as growing, mature or decaying. We can also see the previous storm track in grey and a projected path 1.5 hours into the future in black. The convective rainfall rate product gives an estimate of rainfall rate associated with storm regions. For both products, data is available in near real time every 15 minutes, and previous time steps can be viewed by adjusting the slider or by playing the animation. Future projections of storm motion can also be viewed. The way in which the storm data is stored in the FASTA database allows for high flexibility in its display and utility. One example is the ability for push alerts if a storm is projected to reach the user.
For small-scale farmers, the improved accuracy of this information relative to 24 to 48-hour forecasts could have huge impacts. Warning of an approaching storm could provide time to cover crops left to dry before the rain arrives. They could delay the spraying of pesticides to prevent the expensive chemicals being washed away. Also, they could adjust the transportation schedule to avoid disruption on the roads.
We are pleased to begin piloting this project in Kenya in partnership with the Kenya Meteorological Department. The ubiquitous availability of satellite data means that FASTA could be made available anywhere in tropical Africa or even further afield. FASTA is keen to partner with African initiatives to explore the utility of nowcasting and harness the data in the most impactful way.